Hey guys, this video is going to be a short video on Newton's laws of motion. For homework on Friday, I asked you to read the pages in your textbook about Newton's laws and to write 10 bullet points, so hopefully you've done that. You still should be copying these notes because they're in a lot more detail and they will hopefully allow you to better understand each of the laws. We're going to go over only the first two laws, so Newton's first law of motion and second law of motion, and we'll go over the third on Friday when I get back. Now, like many of the laws of physics, Newton's laws, a lot of people have heard of these laws of motion and they know what they are, they can repeat them. A lot of people actually don't know what they mean, or there's a lot of other people out there, scientists, who don't really believe what they mean. Now, like I've mentioned last class, we're going to go over the simple theories related to each of the laws. And in your own time, if it's something that interests you and we want to look deeper into it, we can, or we can discuss it at some point. But again, I want to emphasize the fact that I'm going just over the basic laws so that you can have a good understanding and that you can be at least exposed to his laws of motion. Now, the laws of motion can be summarized as follows. His first law is basically, and a lot of people just know, they could just repeat this law. It's basically an object that's at rest, in other words, an object that's not in motion, or an object that is in motion is going to stay that way unless it's acted on by an unbalanced force. So again, an object that's not in motion will stay that way, or an object that is in motion will stay that way unless it's acted on by an unbalanced force. We're going to talk about it in more detail in a little bit. Second law of motion basically says that force is equal to mass times acceleration. And the third law says that for every action, there's an equal and opposite reaction. So let's look at Newton's first law of motion in a little bit more detail. It's also referred to the law of inertia. So it states an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted on by an unbalanced. Now, what did I just say, and what does it mean? Newton's first law of motion is also called the law of inertia. And why is it called the law of inertia? Inertia is a word basically describing something's predisposition or something's affinity or its need. So inertia is basically an object's need. Need is a really strong word, but it's predisposition or affinity to stay the way it is. For example, the pumpkins in this picture are going to stay the way they are, okay, and they have this, again, quote unquote, need to stay the way they are, unless there's a force that acts on them. So the pumpkins are going to stay, or your pencil is going to stay on your desk and it's not going to move unless a force makes it move, unless you pick it up or unless you flick it off your desk. So inertia, as stated, is basically the tendency for an object to resist a change in motion or a change in velocity. If something is not moving, it's going to resist movement. It's going to want to stay in that at rest or not moving. If an object is in motion, it's going to want to stay that way unless each of those are acted on by an unbalanced force. Again, so you're playing golf and you hit the golf ball and it's airborne, so it's flying through the air. Now, that ball is going to want to stay in the air, okay? That's what we call inertia. But unfortunately, there are constant forces acting on something that's flying in the air. And for this particular example of a golf ball flying through the air, there are actually two forces acting on it. There's the force of gravity and there's the force of friction or fluid friction. If it wasn't for those two forces, that ball would continue moving. And this applies the same thing. If you have a ball that's just sitting there, a golf ball that's sitting there that people haven't touched, it's going to continue sitting there unless there's a force that acts on it, unless you pick up that golf club and you hit it. Now, this probably all sounds like a lot of common sense to you, but this is what these laws have been based on, these ideas that they've been based on. And it says, why then do we observe everyday objects in motion, slowing down and becoming motionless, seemingly without any outside force? And we've already talked about this. So this is a force that we don't really see, and it's called, okay? And just to quickly review, we've got 4 main types of friction: sliding friction, rolling friction, fluid friction, and static friction. And these are some of the unbalanced forces that act on an object in motion. And remember, we talked about a book sliding across the floor. The book would continue to be in motion. In other words, it would continue to go at that same constant velocity if it wasn't for sliding friction. A perfect example of Newton's first law of motion is you driving in a car, and it's the whole idea behind a seatbelt. Okay, you and the car are going at a particular speed. So if that speed is 80 kilometers an hour, and you're both going at 80 kilometers an hour. Now, if you're not wearing a seatbelt and that car hits a brick wall, then you, who is not wearing a seatbelt, you will continue to go at 80 kilometers an hour, probably right through the windshield and into the wall. Again, this is the whole idea behind seatbelts. It's the same thing that you're on your skateboard and you're going at a particular speed and your skateboard hits a sidewalk. You are going to continue to be flown to move forward at whatever speed you were going at because of Newton's first law of motion. Now, Newton's second law of motion is really quite simple. It says that that force depends on mass and acceleration. Basically, the law says that if there's a force acting on an object, the object will accelerate. The acceleration will be directly proportional to the net force. In other words, if it accelerates twice the speed, that means it's twice the amount of force that's acting on it. However, the acceleration is inversely proportional to the mass. And we're going to look at that in the next slide. And also, you got to keep in mind that acceleration is in the same direction as the net force. We just finished saying that acceleration is directly proportional to the net force. So what does this mean? Directly proportional means that if the force doubles, the acceleration doubles. If the force triples, the acceleration triples. And if the force is half as much, then the acceleration is half as much. Now, the term inversely proportional is the opposite. If the object's mass doubles, that means its acceleration will be half as much. If the mass triples, the acceleration will be a third as much. And if the object's mass is half as much, acceleration doubles. We're going to look at that. This is going to make more sense to you when we look at the acceleration. And I have a couple of really good slides. So what is this slide telling us? This is the actual equation that we looked at before. So the force is equal to mass times acceleration. So if we look at it here, acceleration, if we look at it up here, acceleration, so the acceleration of the object that's in motion depends on the force that's acting on it divided by the mass. And it makes a lot of sense. In this slide, and it's not going to work well, I'll put the PowerPoint on Moodle because this is actually a cute little animation one of my students made last year. And what this was trying to, again, it's not going to work on this program, but the purpose of this was to show you that if you have 3 objects with the same mass, the one that's going to move the fastest, which would be this one here, is the one that has the most force applied. If you apply half the amount of force, like in this one, well, then it'll move slower. And if you apply even less force, it'll move even slower. So this is the idea that force is directly proportional to acceleration. The more force you put on an object, the faster it will accelerate. Now, the purpose of this slide is to demonstrate that if your force is constant, as it is here. So same amount of force applied. An increase in the mass, so an increase in the mass will cause a decrease in acceleration. So the one with the most mass, so the one with a high mass will have a low acceleration. And of course, the opposite is also true. A decrease in the mass will cause an increase in the acceleration as long as the force is constant. A lot of these concepts are really common sense and things that you come across every day. And there's a perfect example of it in your book. They have the picture of a kid pulling a wagon with another 2 kids in it. Now, if you want to be able to pull the wagon easily, in order to increase the acceleration of the wagon, all you need to really do is decrease its mass. So you should basically take the kids out of the wagon, and it'll make it a lot easier for you to pull it. So this idea of Newton's second law, force equals to mass times acceleration, is something we come across every day. So just to summarize, Newton's second law, net force of an object is equal to the product of its mass and acceleration, or simply put, force is equal to mass times acceleration. Mass, just to look at the units a little bit, mass is in kilograms. The SI unit for mass is kilograms. SI unit for acceleration is meters per second squared. Force is in newtons. So basically, 1 newton is equal to the force required to accelerate 1 kilogram of mass, 1 meter per second per second. What does that mean? You need 1 newton, so you need 1 newton of force to accelerate 1 kilogram, 1 meter per second squared. And it's a little hard. You're going to need to repeat it to yourself a couple of times to really grasp it, okay? But if you look at, let me just write it over here. If you look at force is equal to MA, so force, so Newton, is equal to the mass, which is kilograms, times meters per second squared, okay? So you need 1 Newton to increase an object that's 1 kilogram, 1 meter per second squared. The equation can also be used, and I just realized it's written here, but the equation can also be used to solve really simple problems. So if we have a problem that says how much force is needed to accelerate a 1,400 kilogram car at 2 meters per second or 2 meters per second squared, you basically just fill in the numbers and the units and you solve for F. So if we fill in the mass here, the acceleration here, like they've done right here, so 1,400 times 2, it takes 2,800 newtons to push a 1,400 kilogram car at 2 meters per second per second.